All right, you guys. So we were doing linear patterns. We're now going to be looking at 2 questions. After that, we are going to be moving on to our exponential and quadratic patterns. All right. So that one. So here is an example of a past paper question. And this says to you, these are the first 5 terms of a sequence. Find the nth term of this sequence. In other words, find Tn. So with this sort of thing, we need to identify what kind of sequence is it. So we have a look and we see we are minusing 5, we are minusing 5, minusing 5, minusing 5. Therefore, linear pattern. And we know that a linear pattern has the form dn plus c. It could be an plus b. It doesn't matter what the letters are, just as long as you know that d is my common difference and that c was my adjustment constant, and to calculate c, it was T1 minus D. All right, so my common difference, in other words, what am I doing to each term to move from the next term to the next term to the next term? I'm subtracting 5, so Tn equals minus 5n. And then to get my C, I need to take my first term minus my difference. So that is 13 minus 5. Please note the double minus. Do not just go 13 minus 5 is 8, great. No, 13 minus 5, which makes that a plus. 13 plus 5 gives me 18. How do I know I'm correct? Is something you need to be asking yourself right now. Well, I can sub in a couple values. I can sub in n as 1. So then T1 would be minus 5 times 1 plus 18. 18 minus 5 is 13. That looks good. Let me try one more. T2 is minus 5 times 2 plus 18. So 18 minus 10 gives me 8. Good. I am happy with that. So that is my 2 marks. Very nice, very simple. So remember, once again, common difference, what you're doing each term to each term, I'm subtracting 5. My adjustment constant, I told you, is always going to be the formula T1 minus D. In other words, the value of the first term minus my common difference, which was minus 5. And that's my formula. Fantastic news. All right. Then we have another question. Need to select mouse. All right. Find the nth term of this sequence. So I want you guys to take a couple minutes, see if you can find the nth term of this sequence. All right, so we've had some time now. Just now after I paused the video, we've had some time to have a look at this stuff, and we have had many people that are coming up with an answer of 4n. So let's see if they are indeed correct. Well, this we see, we're going to add 4, we add 4, we add 4, we add 4, which means this is linear. Of course, we know it would be linear because I'm not going to give you anything other than what I've taught you yet, which is only linear. So therefore, I know it's Tn is dn plus c. My d is what I do each term, which is 4. So that is 4n. My adjustment constant, T1 minus d. T1 is 4. My common difference is 4, which means it is answer of 0. So it's 4n plus 0. And the plus 0 is irrelevant, meaning that Tn equals 4n. And that makes sense because these are the first multiples of 4. 1 times 4 is 4, 2 times 4 is 8, 3 times 4 is 12, 4 times 4 is 16, 5 times 4 is 20. All right, so linear, they really don't ask very much. They'll either give the next couple terms or find the nth term of this. There you go. They might even mix it in with another question that I will deal with a little bit later, because they had a quadratic pattern, they had a linear pattern, and they had a nondescript pattern, meaning that I think they prefer to call it irregular patterns, but you'll see it when we come across it. All right. So we can now look at our exponential, or sometimes known as geometric patterns. So the difference between exponential and geometric, exponential or geometric patterns and your linear patterns is that with a linear pattern, you are either adding or subtracting term by term. With my exponential or geometric, I am multiplying or dividing term by term. So therefore, I could have a pattern like the following: 3, 6, 12, 24, 48, 96, etc. Now, if I'm just giving you this pattern, you don't know if it's linear, you don't know if it's exponential, you don't know if it's quadratic. So we have a look at the differences. So the difference is 3, it is 6, it is 12, it is 24, it is 48. So it actually forms the same pattern again. Now, this will only happen if I am multiplying by 2 every time. Now, first of all, I know this is not linear. And I know it is not linear because this is not the same. When I get to quadratic, you will see that this next difference in quadratics is constant, just like a linear one is. And because this is not constant, this is not a quadratic. Okay, so how do we then deal with exponential ones? So we've got our example, which was 3, 6, 12, 24, 48, 96. So we have our general form, that is a times r to the power of n minus 1. So this is my formula for the general form of a geometric or exponential pattern. And what do these represent? Well, a represents my first term. R represents my common ratio. And my common ratio is what is multiplied each time to get to the next term. And then, you know, n is n, tn is tn, they stay, because n is your position and tn is the term's value. So in this scenario, we see that my first term is 3. And what am I multiplying each time to get to the next term? Well, here I multiply by 2, multiply by 2, multiply by 2, multiply by 2, multiply by 2. So therefore, this is 2 to the n minus 1. And that is all you need to be doing. It is literally that simple to find this Tn equation. It is, in my opinion, just about as simple as finding the Tn for a linear. You find your first term, find your common ratio, and you're done. What about, I say to you, etc. And I say to you, find my general term. Well, I can see if I check subtraction, if it's a linear, I'm minusing 4, minusing 2, minusing 1, minusing a half, minusing a quarter. That's not going to be a linear. If you do it again, it's not going to be constant. It's not a quadratic. But I see that each time I'm actually dividing by 2. So my Tn, a times r to the n minus 1. So my first term is 8. I need to get my ratio. Now, if I put my ratio as 2, and I'm actually even going to put this as a different color because it is very important to note this point. I put my r as 2 because I'm dividing by 2. I can then sub in a value of n to see if I get the sequence I'm looking for. So if I sub in Tn as 1, I get 8 times 2 to the 1 minus 1. That comes out at 1 times 8, which is 8. And that is fantastic news. So with that being 8, that is 8. Seems good, doesn't it? But remember I said we need to sub in a couple things. So what if we sub in T2? That is then going to be 8 times 2 to the 2 minus 1. 2 minus 1 is 1. 2 to the 1 is 2. Times 8 is 16, which is a problem because we're going in the wrong direction. And the reason we're going in the wrong direction is because our common ratio is incorrect. So we have an option. What if we make it minus 2? Well, if this is minus 2, it'll be 8 times minus 2, giving you minus 16. So yes, you're making it smaller, which is good, but you're still not the right value. So the problem is if you were thinking of doing this, you did not read my definition of what you're meant to be doing in a common ratio. Because the common ratio, I will state once again, is what we multiply each time. So what am I multiplying each time? Well, I'm halving. And if I'm halving, that means that I'm not multiplying by 2, but I am indeed multiplying by a half. So anytime that your sequence is going smaller when it comes to a geometric or exponential pattern, this ratio is going to be a fraction because you are multiplying by a fraction less than 1 to make numbers smaller. If your numbers are becoming bigger, this ratio is going to be a number bigger than 1 because that is how your numbers grow. So if we sub in T1, we get 8 times a half to the power of 1 minus 1. Again, this is a half to the power of 0, which we know is 1 times 8 is 8. So that still works. But when we have a look at T2 is when our important difference comes along. The 2 minus 1 means that we're taking 8 times a half, which is indeed 4. And if you halve that again, you get 2. And if you halve it again, you get 1, which means that this is actually my Tn formula for a geometric or exponential pattern. So it is very important that you don't fall into this trap. You can do one more, which is also very interesting. So what about if I do, let's say, (81 minus 27, 18 minus 9. Right? No, that 18 is not meant to be there. That's meant to be 9. That's minus 3. That's 1, etc. So we can go through our checks. We find that this is a geometric or exponential. So Tn is a times r to the n minus 1. Great. A is 81. There's no problem with that. But now, the question is, what are we going to do about r? So r is what are we multiplying each time? And if you can't see immediately how to find r, you can simply take T2 and divide it by T1. So that is minus 27 over 81. And that comes out at minus a third, which means that this r is going to be minus a third. And we knew that it would have to be a fraction because my numbers are becoming smaller. But also the fact that it's positive, negative, positive, negative, positive, negative means that you're going to have a negative common ratio. So let's check. If we have T1, that's 81, and my minus a third, this is going to become nothing. So we're going to get 81. We know we should be getting 81 because that is my first term. Great. So that doesn't actually help us. T2 is going to tell us if we're on the right track. That's 81 times minus a third. 81 times minus a third does give me minus 27, which means that this Tn is looking good at 81 times minus a third to the n minus 1.